Thank you, Wendy. Thank you, Ingrid. Thank you, the members of the planetary section. It's a great honor, great privilege to be talking with you this afternoon and to be giving a lecture that is named after, probably like many of you in this room, one of my heroes in the field, giant Gene Shoemaker. We're really celebrating a legacy of Gene and his work. And it's something that I talk about in my own classes, for example, and try to tell my students, imagine a world where we didn't really know if those circular features on the moon were impact in origin or volcanic in origin. And of course, this was Gene's thesis work, his life's work, looking at meteor crater and explosion craters of other kinds, and really collecting the mineralogic, morphologic, and other information that allowed us to make that connection between asteroids, comets, bolides, and the features that they create on planetary surfaces. So it really is a privilege to be giving this lecture in his honor. And one of the quotes from one of his pieces of work, "The moon is a record of the history of the solar system," and that is absolutely true. Anybody who does lunar science knows that. And I claim, and many others do as well, so is Mars. Mars is like that in that it preserves much of the early record of the history of our solar system that has been lost from the surface of our own planet, and exhibits many kinds of processes that have analogies with those of our own planet and other worlds. So why Mars? Why Mars? Indeed, right? Lots of reasons, many of which are known to people in this room. Most Earth-like planet accessible for detailed surface study, the accessible part being because it's relatively close to us in the solar system. And then there's what I just talked about, that issue of preserving 4+ billion years of the record of planetary surface and interior evolution, much of which is lost from our own world. Lots of questions that can be addressed with studies of Mars. This is a highly incomplete list, but what determines planetary habitability? Did life arise there independently on another Earth-like world? And what's the relationship between Earth and Mars? And what does studying a place like Mars tell us about the future of our own terrestrial planet? So lots of good reasons to do that. And those kinds of reasons and others have motivated an enormous effort internationally since 1960, 47 different missions by 8 different nations or organizations of nations. By the way, more than 40% have failed, most of the early ones, but it still happens, even in modern times. It's a difficult target to get to. It's a very difficult, possibly the hardest difficult target to land on in the entire solar system. And yet, despite those difficulties, there have been 10 successful landers or rovers that have made it onto the surface. And so today I want to talk about just 5 of them on the NASA side. I want to take a rapid fire, highly selective and certainly incomplete tour of some of the major geologic and mineralogic and geochemical results from these 5 particular NASA mobile robotic labs. And I really talk mostly about mobility as an asset that is unique to these missions. And the way that mobility has been used in these missions is key to allowing them to make, and their teams to make, the discoveries that they've made. And then as I wrap up, I hope you can indulge a little bit of soapbox commentary, maybe even some optimism about the future of Mars sample return, the future of mobile robotic exploration of Mars, and the eventual future of human exploration. So that's the joyride I'd like to take you all on. And it can get summarized here. Since the time of the first landing on Mars, the Vikings in the mid-70s, there's been 30 years of mobility in science on the red planet, starting with Pathfinder, going through Spirit, Opportunity, Curiosity, and Perseverance. So I'll walk through some of the major results and highlights of each of these missions. Here's a nice shot of Sojourner, the little rover that could, the first mobile vehicle on the surface of Mars, next to a computer-generated microwave oven for scale. It was the first Mars landing. The Pathfinder lander and rover was the first landing in more than 20 years in the late 90s. This is a pretty small vehicle, 10 kilograms class, microwave oven size, and total traverse over the entire mission, 83 days on Mars, about 100 meters. And that seems tiny by today's standards and today's metrics of Mars surface mobility. But believe me, those of us who went through it, it was a major accomplishment at the time. The fact that this vehicle could be commanded to move from place to place was so very different than what our experience was on Viking. With Viking, you could reach the arm out and scoop the soil and nudge some rocks and all that. But with Sojourner, and you can see the business end of the alpha particle X-ray spectrometer there in that view on the lower right, it was possible to drive up to these different targets, rocks, soils, crusts, drifts, and make detailed chemical measurements of them. So it was early days of commanding vehicles like this, moving on the surface. Of course, long latency in getting data back and figuring out whether it went where it was supposed to go or not. But overall, it turned out to be incredibly useful to be able to take that resource, that instrument, that elemental chemistry instrument, and deploy it onto a variety of different materials. And here's just an early figure from one of Hap McSween's papers. Great to see Hap in the audience today. You know, this allowed us to really build up the statistics beyond the small number of Martian meteorites that have been known at the time, and of course, petrologic models of what folks think was going on Mars, and put some of these rocks and soils and regolith deposits onto the standard volcanic classification chart, right? Is Mars a basaltic planet? Yes, of course. That's what the SNC meteorites were telling us. That's what remote sensing was telling us from telescopic and orbit up to the time. But now we can actually measure some of those basalt samples, basaltic andesitic samples, maybe even higher silica abundances in some of them. But we could start to have the detailed geochemical arguments because of that mobility that allowed us to collect the sample of this relatively large number of in situ observations. So that was pretty cool. And it really led to a direct evolution to the Spirit and Opportunity rovers, which landed in 2004. Designed for 90 days, designed for 600 meters traverse as goals. They both exceeded those goals dramatically, of course. Cutting edge at the time, imaging and spectroscopy instruments, building upon what had been sent with Viking and Pathfinder, and what was being prepared for orbital platforms, those kinds of sensors. And then really building in mobility from the beginning, you know, not just the lander, but the entire payload, the science payload, the entire thing was designed to be mobile from the start. And the team really regarded mobility as a key resource, just as key as power, telecom, all of those schedule, you know, all the important stuff that you regard as your resources. So these rovers loaded with high-resolution multispectral cameras, infrared spectroscopy, and then a variety of in situ spectroscopic methods, alpha particle X-ray spectroscopy, Mossbauer, which is very sensitive to iron minerals, microscopic imager for up-close views at the sort of 150 to 100 micron scale, an abrasion tool to try to get below the dust and the surface coatings, and of course that mobility. They were a step up from the Sojourner rover in size and capabilities and ambition. So I love these views of folks doing the testing with them. They're all, everybody's in your bunny suit, and it's a super clean room environment, modern day cathedral inner sanctum, and yet they're out on Mars now, just filthy dirty, all of them. But you have to prepare them the right way. So mobility, absolutely key, not only going over obstacles, but going down significant slopes. Nice shot of pre-flight testing of one of the simulator vehicles here, not only going down a 30-degree slope, but over an obstacle like a rock or a ledge on that slope. And we actually had to do these things with the vehicle. So having the test bed capability in the lab, basically, and in the CAD, to be able to model these kind of behaviors is absolutely critical. You can't just have rovers on another planet. You have to have them in the lab too, to make sure they work properly. And then kind of a one-slide summary, and I could let this play for like an hour, but I won't. This is all the front hazard camera images strung together from both missions, Spirit and Gusev Crater on the left, Opportunity and Meridiani Planum on the right. You can see the arm doing its work. You can see the drives, just an enormous amount of terrain covered with both vehicles. You know, one sol at a time, one day's downlink at a time. Rovers go to sleep and everybody on the team stays up, figures out what to do the next day, makes tactical decisions, and then makes things happen. Like I said, I could watch these for hours. They just keep going on and on, but they give you a sense, a rover's eye view of what it would be like to traverse across the terrain. So Gusev, Spirit rover and Gusev Crater. It might have been HAP that coined the term basaltic prison. I'm not sure. Was it really that? Or was it a once habitable environment? We were trying to figure that out as we traversed across the plains of this big impact crater with a beautiful outlet channel in its southern margin. We traversed across the plains and into some hills, some number of kilometers away, which we never thought we could get to. 2 to 3 kilometers away with a 600-meter rover seems like an infinitely far place to go. But we did in fact make it. But when we first initially landed, we were seeing evidence of basaltic volcanic rocks, and I'll zoom in here on Bonneville Crater. Here we go. This is the first large crater that we got to, and using Shoemaker's principles, we were trying to figure out, would we see morphologic evidence or mineralogic evidence of what might have been excavated or created in the impact? Would we see evidence, for example, of shallow subsurface lacustrine deposits that got dug up by a crater like this and strewn across the surface in its ejecta field? We could certainly see lots of blocks and boulders. And so that was, following Shoemaker's idea that, craters are probes of the subsurface, are probes of the past. Maybe we would find those lake deposits. In fact, we didn't. The crater floor plains turned out to be, even in places where they were dug up by craters like Bonneville, mostly olivine-bearing basalts, mostly with textures and mineralogies consistent with volcanic lavas, not lake sediments. And this is what compelled the team to drive over to these hills, which looked slightly different from the then available orbital data, although almost all of this is really dusty from orbit, so very hard to tell. But morphologically, there were clearly some differences, especially in the inner basin beyond this ridge, where there was some evidence of sort of light-toned, circular plateau-like features of enigmatic origin as judged from space. But that assessment of what we saw in the plains came from the so-called squiggly line science on vehicles like this. This is the work of the spectroscopy teams on not just rovers, but landers, orbiters, all kinds of flyby missions, right? It's interpret these kinds of data in both chemical and mineralogic ways. The visible to near-infrared multispectral images showing evidence of the so-called 1 micron band, iron-bearing silicate minerals, olivines and pyroxenes, things like that. The mid-infrared through instruments like the mini tests, allowing detailed abundance modeling of olivines, different pyroxenes, dust components, different kinds of oxides, as well as the in situ instruments on the end of the arm that allowed a highly detailed elemental chemistry from the APXS, and then extremely diagnostic Mossbauer spectroscopy for iron-bearing minerals, also another instrument on the arm there. So we could get at, in great detail, the olivine, the pyroxene, and eventually the iron oxides with that instrument. So it's, yes, the images are spectacular. Yes, they give us lots of details of the morphology, but most of the details of the geochemistry and mineralogy come from these kinds of instruments being deployed at the same time. So when we did get to the Columbia Hills, things changed. We started to see a diversity of aqueous alteration features, multiple distinct alteration facies, including some of the ferric oxides, oxyhydroxides like goethite, bearing rocks detected. Also, identification of relatively magnesium-rich carbonates in some of the rocks that provided some of the first initial evidence that even in a place with such an abundance of sort of dry, volcanic, basaltic kinds of rocks, some environments here, or some places where those environments have been exposed, show evidence for the combination of water and CO2 with those volcanic precursor materials. So really some of both that we're seeing. And this culminated in work around the area called Home Plate, one of those raised plateaus in the inner basin of the Columbia Hills that I mentioned earlier. A large number of morphologic features, fine layering, even some evidence of soft sediment deformation. Kevin Lewis and colleagues did some great work on putting this story together morphologically and mineralogically. It was also extremely interesting because in the shallow surface, we saw evidence of high silica on the left and high sulfur, extensively leached and altered soils. Funny story, we wouldn't have seen these if one of Spirit's rovers wheels hadn't stopped working, but it did, and we were dragging that wheel through the soil, exposing this stuff to view, which we might have just missed otherwise. So sometimes the breaks do go your way. So these are enigmatic, as are these kinds of features. These hydrothermal, putatively opaline silica deposits in both nodular materials and soil materials. Maybe this is probably some of the strongest evidence that we have that this was a hydrothermal setting and maybe a great place for the potential preservation of biosignatures. And I'll just point out that this discovery, and this is work by Steve Ruff, Jack Farmer, and others, it spawned an entirely new mission concept in the biosignature community of workers who want to go back there and look at this material up close. And if you're interested in, learning about that, go look up the Life Springs Mars project being led by Curtin University and international collaboration with Australia, New Zealand, India, and the US. These are really enigmatic features, and it's what helped keep this area on the finalist landing site for the subsequent generation of rovers. Meanwhile, an opportunity in Meridiani Planum, Opportunity is doing a same kind of mission with the same equipment in a very different, completely different place. Hopping from crater to crater to look into the subsurface because the surface itself, is dominated by this low-lying tabular outcrop, while dominated by large expanses of drift and sandy ripples, but dominated where exposed by this low-lying sulfur-rich hematitic outcrop that shows this evidence of these concretions, interpreted as diagenetic concretions that were precipitated, iron reprecipitated after groundwater-driven mobilization. And so there were millions of these little grains strewn across the surface where we could see them. Big surprise. The remote sensing from TESS on MGS had said that there is hematite there. We didn't know what form it would take, and nobody had imagined it would be millions of tiny little spherical grains that are interpreted as nodular concretions. So surprises do happen, and again, proving that those were hematite-rich came from the infrared spectroscopy of mini tests and the Mossbauer spectroscopy on the arm. So again, the morphology is great, but leaves you scratching your head sometimes, and you need these kinds of really quantitative spectroscopic observations to prove the point and get the geochemistry right. This area of exposed outcrops is called the Burns Formation, named after our colleague Roger Burns. Hundreds of meters thick sedimentary sandstone dominated by reworked basaltic sands that litter the plains, sulfates, these hematite-bearing concretions, dunes, sand sheets, and playa facies. It's a really, really interesting place. And we saw that hundreds of meters of section exposed in places like the walls of Endurance Crater. This is where we had to put our engineering colleagues to the test. And we said, look, we need to get inside there. We need to do that experiment that you did in the lab of getting the rover down this 30-degree slope with boulders and obstacles. We need to do it for real on Mars. And so we did it with a lot of help from the testbed folks, of course. And this panorama is now taken from inside Endurance Crater on that slope, which some of the rover drivers described it like trying to drive down plywood covered with ball bearings. So it was a dicey, sporty trip on this part of the mission. And but it revealed, look at those beautiful sandstones and cross bedding there, revealed that the details of the structure of the stratigraphy of the burn sequence down many meters here, and we could see across the walls of the crater down many meters more. So having the mobility to get to those places was absolutely key, right? And it was a little bit lucky in that there are steeper places to go, but there were ways to get down there at 20 to 30 degree slopes. So we couldn't just go anywhere. And here's an example of a place we couldn't ever have gone if it wasn't for the fact that there are some 20 to 30 degree entry ramps to an even bigger crater, Victoria Crater, where most of the ejecta has been planed off by the aeolian erosion happening out in the plains, but leaving exposed in beautiful cross-section this spectacular cross-bedded sandstones of the Burns Formation. So again, being able to get down there and measure the depth of this sequence and this stratigraphy even more extensively was absolutely critical. Just a couple of shots. Again, I could show beauty pictures all day of these terrains, some of those most spectacular landscapes we've encountered on Mars. And then eventually getting into an even larger crater, the rim of Endeavour Crater, about the size of Washington, D.C. Again, most of its ejecta deposits planed off, worn down, eroded away. But some of the rim preserved in places like Shoemaker Ridge, one of the stops that we made on the way out there, driving along the ridge. And here was interesting because we were seeing stratigraphy below the Burns Formation, looking at these older smectite-bearing, vein-filling materials that underlie the formation. And these are much more, the chemistry of these, much more consistent with more neutral pH fluids as compared to the Burns Formation mineralogies, which included things like jarosite, for example, that are typically indicating much lower pH, more acidic fluids. So clearly the environment was changing over time, and being able to access the stratigraphy over the course of this extensive mission was absolutely key in understanding that. Thinking about where to go next, after Spirit and Opportunity, the enormous flood of information coming in from MRO, and Scott Murchie talked about the amazing successes of the CRISM investigation this morning and other aspects of MRO, high resolution imaging coming in, global imaging coming in, spectroscopy coming in across the spectrum, and the continuing spectroscopy coming in from MGS, of course. Folks like Malin and Edgett used some of that imaging to identify this enigmatic class of large craters on the planet. Here's just 4 examples of them. They're all, 60, 75, 100 kilometers in diameter, and they range in morphologic state from nearly completely filled with sediments, like the one in the upper left, through various stages of sediment infill and exhumation to nearly empty, like the one in the lower right. And the one in the lower left is Gale Crater. And Gale Crater emerged very quickly in this kind of analysis as a really interesting place to go look at because it showed evidence of having been a lake at one point in its past, like several other craters on Mars, but it has an enormous mound of layered sediments in its interior. And the top of the mound is actually slightly higher than the rim of the crater, which is a puzzle. And so maybe it's an example of one of these places where the crater had been filled in, like the one in B up above, and it's just slowly being exhumed over time. This concept of craters on the surface of Mars not being a surface process, but being a volumetric process really came out of studies like Malin and Edgett and others in the early 2000s. So Gale emerged as a great place to go and ultimately was selected as the landing site for Curiosity, which landed in August of 2012. One Mars year design lifetime, still working great today, and leveraging a lot of the advances in mobility that were demonstrated on Spirit and Opportunity, which themselves had been sort of pioneered with Sojourner. So the basic rocker bogie suspension kind of model, the ability to go 20, 30 degree slopes, and the ability to go long distances. And of course, both Curiosity and Perseverance, another leap in capabilities from Spirit and Opportunity because they're nuclear powered. They don't rely on solar power like those first two long-range rovers did. And then a very sophisticated payload, again, building upon previous mobile surface payloads, more higher resolution cameras, different kinds of spectroscopy, including XRD, including isotope mass spectroscopy. The SAM instrument inside of the Curiosity rover is itself about the size, maybe a little bit bigger than the Sojourner rover, right? So these are incredibly complex and sophisticated mobile laboratory instruments that are now carried in other APXS, and the ability to do LIBS from the ChemCam instrument on the mast of the rover. So do laser ablation elemental chemistry. So instead of just having to put the arm down on a relatively small number of spots, could use the laser and collect statistically large numbers of elemental chemistry observations in a effectively remote sensing instead of in situ sense. So this vehicle is, as I say, is still going strong, 36 kilometers of traverse as of Sol 4741 from those plains across the dunes and into the lower slopes, and now climbing the lower slopes of Mount Sharp, that central mound of layered deposits. The floor itself, wonderfully covered with cross-bedded sandstones, conglomerates, rounded class, finely laminated mudstones, all of which are interpreted as fluvial or lacustrine deposits that formed in river-fed lakes entering into the basin. So this was a very active area for fluvial geomorphology and geochemistry at one point in time. So real evidence on the floor of this crater that there was a lake and there were fine-grained deposits on that lake. And that evidence, the geochemistry backed up by data sets like from the ChemCam and the APXS, providing the elemental chemistry from a remote sensing standpoint, but also backed up by drilling and collecting the drill tailings, basically, and bringing them into the rover itself and delivering them to the XRD, delivering them to the isotope mass spectrometer for incredibly detailed analyses. 45 drill holes have been drilled and sampled by these instruments so far in Gale Crater since 2012. I think one of the most exciting things to me is that, being able to put that material into the most sophisticated mass spectrometer ever sent to another planet is kind of incredible. And certainly it's, there've been, many of you have seen the publications, there've been detection of organics. The SAM instrument has detected preserved indigenous organic molecules in those drilled samples, the mudstones especially, even including some very recently reported more complex organic fragments. I think it's cool that these are from samples that were taken relatively early in the mission that are kept inside the spectrometer, and the team keeps twiddling the knobs and dials and refining the techniques to make the measurements even better. And they're pulling just incredible signals out of data that weren't possible to process that way earlier. I think it's amazing that every time one of those drill samples is delivered to the vehicle, something fundamentally profound could be discovered. And it seems that apparently some complex organic structures appear to be able to survive on the surface of Mars for billions of years, despite the intense radiation environment and the intensely oxidizing environment. That's surprising to me. Maybe it's not surprising to the isotope mass spectroscopy people, I don't know. But it's surprising to me, at least, because truly the vehicle's not sampling more than that deep into the subsurface, and it's hard to believe that even that deep in the subsurface could escape billions of years of hard solar UV. But apparently there are places where that can happen. And so it's super exciting to see these kinds of approaching potential biosignatures get teased out of the data. And of course, Curiosity is continuing its adventure up into Mount Sharp, officially called Aeolus Mons, the lower layers containing evidence of clay minerals, a wetter kind of environment where most of the lake water was hanging around. The middle layers, more drier conditions dominated by sulfates. The very uppermost layers could be yardangs or other dust and wind deposits that represent modern day Mars. And so it's really that this rover's driving up that transition from the Noachian to the Hesperian, maybe from the warm and wet Mars to the cold and dry Mars. And that's a very exciting adventure to follow along with. I think the vehicle is actually up in these mesas and buttes now, which is very, very exciting. So that traverse up section has encountered fluvial lacustrine lower units, more arid aeolian and fluvial dominated upper units, but there have been sort of transitions. It's not a hard and fast boundary according to what the rover team is seeing. And there's lots of great efforts to do the mapping based on the the geochemistry of each layer going up, the morphology of each layer going up, all of the detailed quantitative data that can support the morphologic mapping, both from the surface and from orbit. More recently, some of these beautiful examples of groundwater, these veins and fractured mineral-filled veins with sulfate-bearing minerals. And then most recently, many of you saw this surprising evidence for elemental sulfur exposed in crushed rock interiors. There's lots of sulfates around, but this is elemental sulfur sitting in one particular part of that channel. So some fun head scratching going on there. And it just goes to tell us that the exploration is continuing in Gale Crater as we head up that transitional section. And then the final vehicle of those 5 I mentioned at the beginning, the most recent landed in February 21, Perseverance in Jezero Crater. Primary mission, collecting cache samples for Mars sample return, right? This is the first part of the Mars sample return mission that was first called for in the not current but previous decadal survey and amplified as high priority in the current decadal survey. Also nuclear powered, also 1 Mars year design lifetime. It could be fit into the budget. I was told by John Grunsfeld and others that it could be fit into the budget because it's made mostly from 90% spare parts from Curiosity. So that's how Perseverance came to be for the available funding at the time. It leveraged Curiosity for its mobility system, better tires. It didn't get ripped up. That was one lesson learned. It leveraged Curiosity for its payload to have complementary, some similar and some complementary payloads that weren't carried on the first vehicle, but that could reveal new information in a similar kind of a Crater Lake landing site. For example, there's a ground penetrating radar, a RIMFAX, a Norwegian instrument that provides spectacular subsurface scans of layers and contacts. There's, in addition to the LIBS capability, there's a Raman capability on there, remote Raman capability, and ultraviolet spectroscopy and organic chemistry analysis on the arm, an advanced APXS instrument that doesn't take just a bulk 3 centimeter measurement, but can actually take images of the chemistry at an elemental scale, which is phenomenal. So all of these tools representing sort of advances in the decades since the tool kit had been selected for Curiosity. And then of course, and I'll talk separately about it, the Ingenuity helicopter tech demo was carried by Perseverance to the surface, sort of representing a fundamental sea change in the kinds of mobility that I've been talking about. So the Perseverance went to Jezero Crater, another crater lake, this one with a beautiful fan delta on its western periphery, an inlet channel on the west, an inlet channel on the north, an outlet channel on the east. The height of the outlet channels tells us that the crater ponded with water. There was standing water that filled some volume of the crater up to for some period of time, and it was probably that standing body of water that produced the putatively gentle depositional environment to create this fan-shaped delta, this lacustrine delta. So rover landed right off the end of the delta, out in the plains here, drove up onto the delta, up into the channel, over the crater rim, and now is in the Noachian terrain outside of the crater rim. So it's been just an incredible adventure with this vehicle. The crater floor turned out to be igneous, shades of Gusev on this one. Surprisingly, the morphology, the mineralogy, the geochemistry from that instrument payload are all consistent with igneous deposits, including coarse-grained, evidence for coarse-grained, slowly cooling mafic cumulates and overlying volcaniclastic rocks with only minor alterations. Some examples in the morphology here. We saw similar examples in the multispectral imaging, again, looking at the 1 micron band. We could see similar, even better evidence in the elemental chemistry for the places that we sampled up close. We took a couple of samples of this stuff because if it really truly is a volcanic unit on Mars, then it can be, the crater counting can be tied to this particular unit with those samples, if we can get those samples back and age date them. So it was a surprise to not be able to see, and maybe a disappointment to some to not see lake sediments in this area, but also it kind of checks the box for what we need samples to do, and that is do some fundamental Mars age dating and the calibration between crater counting and absolute age dates. That beautiful delta turned out to be an amazing place to explore. This is one of the distal fragments that is separated from the delta called Kodiak, and you can see this sort of classic Gilbert delta, foresets and bottom sets, and cross-bedded like structure here, and higher resolution imaging from the RMI instrument on the SuperCam provided just wonderful stratigraphic relationships, but also evidence of pretty big boulders, pretty big rover size, rounded boulders among these deposits. So this is work that Nicola Mangold and others have led, looking at and coming to the conclusion that it wasn't just a simple quiescent fluvial, lacustrine, gentle deposition of mudstones. There were some pretty violent events, probably multiple events, that came coursing down that channel, delivering very, very large boulders and clasts into the deposits in the delta below. So it's a complex history. Surprise, surprise. It wasn't as simple as we thought it was going to be when we first saw it from orbit. We've also seen beautiful examples of sort of point bar meander systems being recorded in the morphology as the ancient river pulsed and avulsed coming out of the apex of the delta where the channel meets the crater rim, the crater floor. So both the morphology and the geochemistry are pointing towards really interesting and complex hydrologic history of this area. So you've seen the sort of evolution of mobility on these kinds of vehicles from this smaller, compact Sojourner to the mid-sized Spirit and Opportunity to the more monster truck Curiosity and Perseverance vehicles. Well, the sort of next step to take the next leap in sort of off-planet mobility meant having to take a jump in the air, right? And that's what the Perseverance rover carried. The Ingenuity helicopter mission was a demonstration of a next step that one could take in the evolution of Mars mobility. And here's the historic first flight as recorded by the Mastcam-Z instrument, lifted a whole bunch of dust to get up into the air, came down and set interplanetary aviation history in April of 2021. Under 2 kilograms, solar powered. Those rotors are going 2,400 RPM to get even just that small Kleenex box worth of mass up into the air in the thin Martian atmosphere. Here's a time-lapse video taken by the rover's own navigation camera during its 4th flight. It was sent over some very fine-grained regoliths, some ripples, and sandy deposits, place where we were never going to take the rover itself because it probably would have been too challenging to drive over. So it was sort of starting to test the process of using this vehicle as a scout. You send something like this to places where you know you can never go with a rover or with a person, collect images. If you can make it carry a little bit more mass, you could maybe do some spectroscopy or some GPR, other kinds of experiments like that. So in that sense, it was a great demo. It was supposed to fly 5 times. It flew 72 times, so far exceeded its lifetime and collected just a cornucopia of data for the engineers to think about not only the sort of Martian winds and thermal environment that vehicles like this have to deal with, but thinking about the ways that it could support scientific exploration. And so one can imagine future advances in mobility based on those kinds of systems. There's a concept out there called Skyfall that's being worked on between JPL and AeroVironment. AeroVironment, the company that did a lot of the work on Ingenuity with JPL, and the idea there is use a sky crane-like deployment, except don't send a lander down, drop a bunch of copters down and have them all, disperse across an area that you want to characterize in great detail relatively quickly. So the idea of using sort of swarms of multiple kinds of copters like this, that's a great idea to think about. The concept of fixed wing gliders, near and dear to Wendy's heart, I know. The idea of gliding across Mars, an idea that goes way back. But it's possible to do with enough wingspan. There's enough atmosphere there to fly vehicles like that. And of course, you can do other kinds of mobility on the surface, like the JPL eels concept, or other ways to crawl or hop or balloon across the surface. So I'm pretty excited about thinking about ways to do this, to utilize the experience of the advanced mobility that's been demonstrated from rover to rover now, and capabilities of routinely driving hundreds of meters a day now with auto navigation and probably ultimately the use of AI in these vehicles. But not only that, but being able to use these airborne and novel, innovative surface assets to get down there and do this work in different ways. I'll put in a plug for the poster session tomorrow morning on aerial exploration of Mars. So check it out and learn a lot more about these kinds of things. Okay, back to Jezero, and I want to talk explicitly for a few minutes about samples and sample return. And potential biosignatures, right? Indigenous organic signatures, talked about them from Curiosity and Gale Crater. Well, Perseverance has also detected them in Jezero Crater. In addition to those organic signatures, there's evidence for compelling morphologic, mineralogic, and redox kinds of patterns that have been detected in some of these fine-grained mudstones in that channel that fed the delta. And here's maybe the most famous one from a paper that Joel Hurwitz and colleagues on the team put together relatively recently in Nature. This is a close-up Watson view of one of the samples, or one of the sample regions from which a sample was collected in the Ret Vivalis there, on the floor of that channel. And these features are reminiscent of what the geomicrobiologists call reduction spots, places where on Earth, microbial life has created a boundary, an interface between the outside and the inside, and they're using the electrons in iron 3+, for example, to create energy to power their respiration and other activities. And There's the similar kinds of morphologies, similar kinds of sulfur and phosphorus bearing minerals in this environment that have been detected on Mars. And look, the team is not saying these are biology, these are evidence of biology. This is the classic definition of a potential biosignature. It's got morphologic similarities, geochemical similarities, mineralogic similarities to something on the Earth that is of known biologic origin, and makes you go, we should go back and take another look. Or in this case, there's the sample of it on the left in this Mastcam Z view. You can see that we've got some of those leopard spots and poppy seeds and those minerals. They're in there. They're in that core sample, sitting inside the rover right now. And so, yes, we could go there and take a better look, or we could bring that sample back and the others that go along with it and take a better look. And there are a bunch of others. There are approximately 30 samples collected so far, including 3 witness samples, including some atmospheric samples, including some regolith samples. The rock samples range from minimally altered igneous cumulates and regular old volcanic rocks to cross-bedded deltaic sandstones, mudstones, laminated lacustrine mudstones, regolith atmosphere witness samples. It is an amazing set of samples. It is very carefully selected, very carefully documented in context, in stratigraphy, and in everything that we can throw at it with this vehicle. So it's really an incredible collection of samples. And, is it surprising that I'm up here saying that sample return is needed? That's why sample return will change everything. This audience doesn't need to be convinced. But, if we had those samples in hand, we can do the isotopes, right? We can get the absolute ages. We can tie the absolute ages for some of these units to crater counting ages. We can do the trace organics that are required to really nail these biosignature or not claims at parts per billion or trillion. We can do the nanometer scale microscopy. We can analyze these, look at the Apollo samples, right? We can analyze these with techniques 20, 30, 50 years after they come back to the Earth that aren't even invented yet, right? Who knows what will come out of them. And another one, this is not a quantitative, but it's qualitative, but there is global scientific and technological leadership awaiting those who do it, right? So we have to bring these samples back. We have to bring these samples back for a bunch of scientific reasons and others. Current status, well, this is an understatement. The architecture is stalled and under review, right? Those of you who follow along know that it is kind of a mess right now. But that doesn't change the fact that we have incredible samples there. Doesn't change the fact that there is already a depot on the surface of a subset of them, of 10 of them, and there are still about 10 tubes approximately to fill that the team is working very hard to collect from primarily the Noachian basement outside of the crater. There were 2 finalist landing sites, one where we went inside the crater and one outside the crater in the Noachian basement. Because of the mobility and the longevity of the mission and the vehicle, we're essentially able to do a lot of the mission, that second mission outside of the crater in the ancient Noachian terrain, and collect those samples in addition to the primary mission inside the crater with the lacustrine and deltaic samples. So that's what the team is focusing on, is collecting the best possible data set so that there is a best possible collection of samples sitting there waiting under incredibly strong scientific and maybe even geopolitical justification for us to go get them and bring them back. In the meantime, there's so much that we still don't know, right? I had fun with AI helping me make some of these final graphics, so I hope you indulge me a little bit. I don't know what the hell this is, but it came out really cool. This was Claude, Opus 4.5 did this for me. So there's still so much we don't know, and I'm not going to go through all these questions, but I'll just barrage you with them, right? How do we best use remote sensing data to plan surface missions, given that where we have explored, for example, phyllosilicates, sulfates, and crystalline iron oxides, they are more widespread and stratigraphically nuanced than orbital data alone indicated. Scott talked about that this morning in his presentation, right? I think maybe we need a little hubris on our remote sensing interpretations. You get down onto the ground, and sometimes it's not quite the same story. But that's the real story when you get down there. I could go through all of these. How long were these environments habitable? Where are there other potentially habitable Gale and Jezero environments where we could find that evidence for chemical building blocks, energy sources, liquid water? How well do biosignatures survive, right? Is what Curiosity is finding, is that typical? What's the history of volcanism, subsurface water? How'd the climate get to be where it is? Oh my gosh, I mean, I could go on and on. I stopped when I filled a slide, right? I could go on, and hopefully this covers a lot of the research areas that many of you are interested in. And it's sort of finally, these advances in mobility and capabilities for surface directed science that the robotics community has developed over decades now is going to be, I believe, supremely impactful on human exploration. I think it's not a question of do we send people or robots. I think we have to send people and robots. I know a lot of you in this room believe that as well. Certainly robots and robotic precursors give us site selection. They can map out the hazards. They can help identify the resources, but as humans, we're adaptable. We have intuition. We can choose perhaps the best samples to select. We can perhaps repair equipment better than the robots can. So there are some advantages to being people on Mars. And really the best model is synergistic. Robots extend human reach, humans extend robotic capabilities. I firmly believe that. And there are lots of resources that do need to be characterized by a combination of robotic and human explorers. And the timeline, it's not too early to think about human Mars missions in the 2030s and 2040s. And for example, you can see this report from the National Academy. Where's Lindy? Lindy and her team put a great report together. It just came out called The Science Strategy for the Human Exploration of Mars. I think that's a shining a light on what we need to do to get people out there. So thank you for pulling that together. It seems like it's always just too far away, right? But this is the community that has to start thinking about it. This is the community that has to start making that happen, because if we don't dream it, thank you, Claude Opus 4.5, others will, right? I think we have to, it's our responsibility to be optimistic about it. Yes, it's going to take a while. Yes, there's so much more that we don't know than we do know, but I think that the path is clear, and I hope you'll all stay on it. And bring your robot dog. So last slide here, I just want to say thank you to all of my friends, mentors, and colleagues over the years. There's been a small number of us who've been absolutely privileged to be on these 5 NASA voyages of mobile surface exploration on Mars, and it has just been a blast. I also want to just shout out to all of those of you and others who are working on the orbiter teams who relay the surface data back for us at the cost of your science investigations, data volume. It is greatly appreciated. And being the beneficiary of most of those pixels, because most of them are imaging pixels, I especially want to say thank you to the teams from MRO and Odyssey, TGO, Maven. Maven, please call home. Maven, your friends are looking for you. Call home, let us know you're okay. So that's been wonderful as well. Also, I'll just leave this up here. I want to especially make note of the many, many friends and colleagues and mentors who aren't here anymore, but who've been an important part of my journey across the surface of Mars, and I think an important part of many of your journeys as well. I miss many of these people. I worked closely with many of these people, including Gene and Carolyn Shoemaker. I actually worked more closely with Carolyn than Gene on an undergraduate project, but got to know Gene early in my career, late in his career. And I think he would have, both he and Carolyn would just be giddy with all the things we're finding about Mars and other places all across the solar system. So again, thank you all very much. Please come to the microphone if you have questions. Yes, sir. Uh-oh.
Check, check. Nick Schneider, University of Colorado. Thanks to the shout out for Maven.
I can't hear you because the speakers are pointed that way. Nick, just yell.
Closer to it?
Yes.
Oh, great.
Yes.
So you've been through the age of imaging from the small number of pixels to vast number of pixels, and I think the Mars rovers have just had this great episode of bringing Mars to humanity. What's next for that, and will we survive the AI age?
Will we survive the AI age? I could give an authoritative answer to that question. No, it's a good question. And what are the capabilities that we can bring? It's going to depend. Strangely, it's going to depend on our infrastructure, right? It's no good to bring a 65 megapixel video camera someplace where you don't even have dial-up internet. And if you don't know what dial-up internet is, I can explain it to you later. So, bandwidth is going to be required to leverage the sort of crazy advances in sensor technology that are happening. So, luckily, the trend is going in the right direction. We can get, hundreds of megabits to a gigabit back from Mars every day now. When I started my career, it was, hundreds of kilobits to a few hundred megabits if we were lucky. Yeah, and and then AI. I mean, one way to solve that bandwidth problem is to do a lot of the processing on board and not send all that data back. And so, lots of people in the community, including a number of students and postdocs I've worked with, are working on, we call it machine learning, but I think that's basically AI, right? Ways to train algorithms to sweep through data sets to send back parameterized results instead of the original data. It scares the hell out of me, honestly, because of course I want my fingers in the data, right? But there's a subset of what we do that can be parameterized, and probably at a significant savings of data. Scott Merchant has talked this morning, talked about many of those ways that data sets are parameterized. I showed some examples. So I'm hoping it's going to be a sort of creep up on it rather than just completely jump into it kind of activity. But I think there are some ways that machine learning kinds of algorithms can be beneficial. Yes, Dr. Bishop.
Hey, Jim, great talk. It was so fun to see the transitions over the last 20, 30 years of, of how the rovers have come along. And my question for you is, for the next rover, what would you love to see? What kind of instruments? I would love to see a spectrometer on a drone personally, but I'm sure you have a lot of great ideas, and I'd love to hear what you think. I guess for Mars or another destination, what would you love to see on the next rover?
Yeah, what would I? Well, first of all, I'd love to see a next rover. That would be great. And my answer might be controversial with some, but it goes back to an idea that when we were debating at the sort of MEPAG level what to do after Spirit and Opportunity, and go sort of bigger and nuclear and Curiosity and all that kind of stuff, or somewhere else. Ken Edgett and I were pitching to headquarters the idea of sending 10 or a dozen Spirit and Opportunities all across the planet, because there were so many environments that we could say to ourselves with the then available data, in the mid 2000s. Hey, this could be interesting. That we've never seen one of those up close. This is familiar but Martian. And if you could get, a place like JPL into a mode of mass production and lower the cost, you could probably fit maybe at least 5, if not 10, Spirit and Opportunity class, MER class vehicles into a, Curiosity and Perseverance kind of budget. That was our claim. I still think that would be a great idea. And maybe this is an area where, we're talking about potential commercial opportunities to go back to Mars like they're doing at the moon. Maybe there's this sort of mid-size crossover vehicle class, Mars rover that doesn't need to be billions of dollars, but can be, hundreds of millions, which are sort of Discovery New Frontiers class, but done as a program that is intended to really try to sample the diversity of the planet in a way with modern versions of a limited set of payload instruments, like those carried by the current rovers. So certainly if there is a emerging commercial Mars payload program that's with associated landers or rovers, mobile vehicles, I would certainly be pitching for something of that scale, of that class, with the goal not just to go to 1 or 2 places, but a similar goal that the CLIPS mission has on the moon. Let's go to a dozen places. Let's check out all these different environments and really sample the planet's geomorphology, geochemistry, mineralogy in great detail. That's where I would go.
Oscar Combs, Caltech. I was wondering, since I'm working mainly on orbital data, is there something from your expertise from robotic missions, what you would tell people working on mainly orbital data that they should know from the surface?
Something, yeah. So one interpretation of my presentation was don't believe your orbital data, but I don't really stand by that. I think just be careful with it. I think the reality is that when you see the surface at hundreds of meters or even tens of meters scale, there can be a lot going on in that even 10-meter size pixel on the ground. First of all, on Mars in particular, it can be covered with dust and you have no idea what's really going on. And so you would only have the morphologic clues at that 10 meters plus scale. But I think maybe one thing that everybody can do is use the fact that we've got these 5 sites where we have been on the ground. And we do have the orbital data, really the best orbital data for those 5 sites, partly why they were selected, because they're cluster bombed with the remote sensing from orbit to pick them in the first place and then track the missions over time. So there are these great data sets now that can link orbital and surface and can tell you for different kinds of environments where you can trust those linkages and where you shouldn't trust those linkages. And so maybe as a community, it's that's an exercise to go through to convince yourself that if you want to go somewhere else, how does this fit in with my previous experience of linking what I see from orbit to the ground truth that I've got with my wheels in the dirt?
Hello, Elisa Dong, York University. I was actually
Could you speak very closely to the microphone?
Is this close enough?
Yes.
Okay, brilliant. We're like kissing. Yeah, Elisa Dong, York University. I was hoping to hear a little bit more about your thoughts on MSR, human exploration, and your controversial thoughts, if any. But specifically in the current age, you mentioned geopolitical benefits. None of us here are probably politicians. So what is it that scientists can actually do to sort of kick off the next space race and encourage politicians to invest more in, science return?
Yeah, that's a great question. Luckily, you don't have to take my word for it. You can go read the very studied thoughts of thousands of colleagues in 2 different decadal surveys to understand just the theoretical potential of bringing samples back from Mars. What I feel that the folks on Perseverance team and even Curiosity team can add is the reality of we actually have some of those samples, some of those classes of materials that we need to study in more detail and understand the basic fundamental Mars as a planet, geologic history, kind of volcanic sample stuff, and then the fluvial, deltaic, ancient Noachian, right? So it's gone from MSR has gone from being a theoretical exercise to the first part of it is almost done, and that is the collection, right? So we've invested an enormous amount of our scientific capability, national treasure, what have you. Other nations are in it with us to collect this amazing set of samples. There's a big sample community that works with Apollo samples, meteorites, asteroid samples now, and they fill lecture halls and conference room halls and textbooks and journals with just incredible results that can't come from flybys or orbiters or landers or rovers. You have to have that material in hand, and you make giant leaps in your understanding of the history of these places, the processes that are going on there, and the implications for others of that class of object and our own planet and our own lives as well. So there's all kinds of reasons. It is hard. It is expensive. It is challenging. It's a difficult message to get across to the general public. I work with an organization called the Planetary Society, where we take that as basically job number one, try to get the general public, the space-loving public, and our stakeholders in Congress and the administration in the US to understand the value of the investment that this nation has already made in collecting those samples and the payoff when it comes back, the scientific leadership and the sort of perceptional, global, geopolitical leadership of being the first to bring samples, well-selected samples back from planet Mars. So many different angles to this, and the angle you take depends on the audience you're talking with. I encourage you to go look on the Planetary Society website. You don't need to be a member to use the resources. You can contact your members of Congress. You can write letters. You can read lots of talking points about advocacy. There's pointers to the different scientific documents that are involved that help do all that. So there are steps that individual scientists can take. There are many planetary scientists who are members of the Planetary Society, for example. We had something called a Day of Action in Washington not long ago, where we got 300 members of the society on their own dime to come to Washington and talk to their members of Congress about how important NASA is. And there was maybe a dozen professional planetary scientists in that group who took the day off work because it was important enough to come do that. So there are ways to get involved. There are ways to advocate, make your voice heard. The work we do is under attack right now, frankly, from our own government. And so if we don't say something, if we don't speak up and defend it and point out how it is justified, how it does matter in everybody's lives, then nobody's going to do that for us. Thanks for the question.
Thank you.
Thanks.